Hi, within this lecture we're going to start talking about the qubits and the qubit states. So we're going to represent the qubit states in a column matrix or in a vector like we have previously discussed. Okay, so far we have talked about spin down state, spin up state, and qubit down or qubit up or 0 or 1 state. So we have to understand how we can actually represent this in a vector or a column matrix so that we can actually use that column matrix to perform some operations like putting into a superposition or entanglement with using quantum gates and so on and so forth. So in order to understand that, we first have to understand the 0 state and the 1 state. So 0 state, the left hand side, as you can see, classical bit 0, is actually this column matrix, which is the vector. Okay, so we can call this spin down like this, okay, and the other one spin up. So if we see 1 0 like this, it represents the classical bit 0, and I'm gonna tell you why this happens. Okay, don't worry about it. Just so you know that if we see 0 1 like this in a column matrix, in a vector, we know that it represents the state 1. So I'm gonna show you this quantum circuit composer later on, okay, so you don't have to find it or open it right now. We're gonna see how to open it. But just so you know, we're gonna work with qubits, and this sphere you see over here represents a qubit, and as you can see, we can see the state, we can see the vector popping up in the 0 state, okay, and this notation is called cat notation. We're gonna see it later on. And don't worry about it. Again, we're gonna come back to circuit composer. The idea over here is that we can actually see these vectors pointing up to 1 or pointing down to 0, and they represent this column matrix. Okay, so this will be called qubit down state. Okay, so this is the qubit down state. So for example, I'm gonna add a NOT gate, and you don't know what a NOT gate is, you will learn about it. And as you can see, when I do this, it actually went down and it pointed through the 1 state, and as a 100% probability, I'm gonna get 1 out of this calculation. So of course you didn't understand what I just said because we haven't learned them yet, but I'm just saying that we're going to visualize everything over here. Don't worry about it. Just right now you have to understand we're actually going to work with vectors, and vectors, by vectors I mean of course the column matrix, and in the column matrix we have 2 numbers for only 1 qubit, of course. And the upper number represents the probability of spin down, and the down number, the number below over here, represents the spin up probability. Okay, so if we see 1 0, it means that we're gonna get 100% spin down over there. Why this happens? Because we have some number over here, let's call it P and Q. So if we want to just get the square magnitudes of this, we can just get the P squared by just summing up the A squared with B squared. And if we just square these numbers, like get these squared magnitudes and just sum them, then we should have 1, okay, because it's either gonna be spin up or it's either gonna be spin down. So we know that this should actually add up to 1, like add up to 100%. So if we see 1 0 over here like we have seen before, then it means that it's 100% of the time it's gonna be spin down, or like the qubit 0 state or the classical bit 0 state. And if we see something like 0 1, then we know that it's going to be 100% of the time 1. And it doesn't even have to be 0 and 1 because we are talking about qubits, not regular bits. It can be in a position like this, 1 over squared 2. And if you just do the math, if you just square them and just add them up together, it actually goes to the 1, right? And we call this vector in superposition. So this is a superposition vector. Why? Because 100% of it all adds up to 100%. And in fact, there is a 50% of chance of getting a 0 or 1. So remember this. This is spin down, this is spin up, and we also have a superposition, or we can have anything in between as well. So again, we're going to come back to the circuit composer. We're going to have some operations. We're going to see the vectors over here, like visualize the vectors, and we will understand this in a much better way. So just so you know, we're gonna use this information like a lot later in the course, but we're gonna have to see this right now because it's very connected with the subject that we are seeing right now, because it's very connected with the spin measurement. So if we are to measure the spin of an electron, then we should actually have an apparatus to measure this, okay? So in real life, we can have some kind of magnets to measure this, but over here I just drew like an arrow in order to just represent that apparatus. So over here we have the state of the electron, so this is spin up. Of course we don't know it, but it's in the superposition, but just assume that it's in the spin up, okay? And the alignment of the apparatus actually affect the measurement as well. So if they are perfectly aligned with each other, then we're gonna get spin up like 100% of the time, okay? But if we rotate the apparatus in a way that they are not aligned, they are not perfectly aligned, then it will decrease the chance of getting the spin up measurement for us. Of course, we're not going to change the apparatus or some kind of measurement alignment in the quantum computation or in quantum computers, but as you can see in real life, if you actually reverse the apparatus, then you're just going to measure down. Or for example, if the electron is actually in the spin up, then you're going to measure spin down. So in fact, as I said before, we're not even going to change the alignment of the apparatus or something like that, but we're going to change the vectors, like we're going to see something called phase, okay? And it will be affecting the measurements in a way that we can get some different results for our measurements, and we're going to see what it is later on. Just so you know, you have to understand this, because right now I'm going to show you if like an apparatus is aligned with the spin, how can we actually calculate that we're actually going to have 100% result over there. Okay, of course there is a way to do that. You can just multiply some matrices in order to find the 100% possibility, and we're gonna use that kind of multiplication a lot, so that's why we are seeing this. So it happens that we can actually represent them in the spin up phase, like our spin up state like this, okay, 0 1 0 1, A being the apparatus, E being the electron itself. So if we want to calculate this possibility, then we're gonna have to take the inner product of this. So it means that we're gonna have to just take the adjoint of this A and just multiply it with the E. So how do we get this dagger or plus sign, or how do we just calculate this? Of course, we're gonna get a transpose, and we're gonna get a complex conjugate. So getting the transpose is very easy at this point. So it's 0 1, and E is still the same. It's 0 1 again. If we multiply this, we're gonna get 1. So 1 squared 1 is actually the 1 itself. So 100% of the time we're gonna just get this result. So it happens that we can see this kind of multiplication or kind of operation a lot, and again we're just going to have to keep in mind that if we have some kind of rotation in the spin or rotation in the vector itself, then it can have an effect on the measurement. So again, remember, this represents the spin down probability, Okay, and this one represents the spin up probability. That's all you gotta understand through this lecture, by the way. And if we want to just take the square magnitudes of this and just add them together, we're gonna end up in the 1. And again, we're gonna see that kind of operation a lot, and we're gonna see this kind of matrices a lot as well. So there is like a much more easier notation to work with. It's called bracket, and it will help us just represent the states like with this kind of notation over here. It would be very helpful when it comes to advanced quantum computations. So let's stop here and see that bracket in the next lecture together.